There we go. I will begin with a word of prayer. Since I get up here. Eventually. Dear Father, we thank you for this opportunity we have just to meet and study your creation, and just pray that you be glorified in what we do this day, Lord. In your name I pray, Lord Jesus. Amen. All right, so here's my, I don't know if I posted this yet or not. This is the solution for mission 2. It might be good to just sort through here, look at these. So, as I said, you really do need to look at this and compare your solution to my solution, see, did you miss out on like an easier way or something, you know? Because just because you found a logically correct way doesn't mean it is the correct way, right? Like, certainly you could show that W is a subspace in problem 17 by showing it's closed under addition and scalar multiplication, but this would be the wrong way, because it is far, far more logically efficient to just write it as that span, and span is a subspace, so yay, proved. It's kind of very little bit anticlimactic, but that's it, you know. Problem 18 is not a good test question because it would take 2 pages to write out, and it's nothing that's really very difficult. It's just writing a lot of writing. So everything here basically rests on using the definition of a vector space for V and W respectively, and then following through how that attaches the Cartesian product of V and W to make the so-called product vector space. So there it is. But it is, of course, important to know the definition of the Cartesian product of 2 vector spaces and how to work with it, because that's very potentially a kind of test question I would ask about, right? Like, you've seen it a couple different places in the homework. It's something you should know about. How do we define the Cartesian product of 2 vector spaces? What do? We just take pairs of vectors, one from each space, and how do we add each pair, each component, according to the rules of each space that they came from, right? It's very straightforward, but it's also kind of weird, right? Like in your homework quiz that you just did, you had a problem where you had a pair of like a polynomial and a 2x2 matrix. It's kind of weird, right? But we can do that. Now this one here is a good test question because it's a pretty straight down the middle subspace question, right? You've got 2 vector spaces, you calculate their Cartesian product, and you got subspaces for each vector space. Show that the Cartesian product of the subspaces is once more a subspace of the Cartesian product. So this is just a pretty straight down the middle standard subspace question, right? How does the logic go here? I show zeros in there, where 0 is 0, comma 0, you know. I note that the Cartesian product of the 2 subspaces is a subset. We need that. Then I pick 2 elements in the Cartesian product and a constant, you know. And then I write down what that means. That means that x is this pair and y is that pair. And the first component's from the first space, the second component's from the second space. And then I note what I have logically. Since W1 is a subspace, the linear combination of the first elements is in the first space, and the second elements likewise is in the second space. And consequently, when I look at the pair of linear combinations, right down there, I've got something that's in the Cartesian product of the 2 spaces, and as such, Cx plus y is in the Cartesian product. But that shows that Cx and x plus y are both in the Cartesian product of the subspaces, which then by the subspace test proves that it's a subspace of the Cartesian product of V1 and V2. It's a lot of saying. It's easier to write than it is to say. Yeah? Okay. Let's see here. This one, problem 20, I've forgotten what the question was. Oh, here it is. Someone has attached a problem sheet. How handy. So part A, show S is not linearly dependent. So to show something's not linearly dependent, you can furnish a linear dependence. In this case, I just looked at it and saw that there's a relation between those two like that, which shows me that I can write this one as that linear combination of the other ones, which shows you that it's not linearly independent because it has a linear dependence, right? That was one viewpoint we had. What was the other viewpoint? That if we took a linear combination equal to 0, there exists a non-trivial solution to that, right? We proved that that is equivalent to saying that you can write one of them as a linear combination of the remaining vectors, right? That's the kind of thing you ought to be able to prove on a test too. Like that equivalence of those two notions is something you should be able to prove if you're asked. Because the proof of it was pretty simple. We just said, well, if it's a non-trivial linear combination, there has to be a coefficient which is non-zero, so we can solve for that vector, basically. That was essentially the proof. Let's see here, find a basis. So to find a basis, we have to find a linearly independent spanning set. Since I know that the other vector in the 4 is a linear combination of those 3, logically I can throw it out and just keep those 3. If those 3 are linearly independent, then I've got a linearly independent spanning set because of what I already learned in part A. That was my logic here. So, yeah. And I know it's possible because we have general theorems that we proved in the Zorn's lemma day, right? That it's always possible to take a spanning set and reduce it to a linearly independent spanning set by removing vectors, right? And it's always possible to take a linearly independent set, which is not a spanning set, and adjoin vectors until it becomes a spanning set. Like both of those things are possible. The question is, how do you actually do it for actual example, right? So here's how I did it there. It's been a minute since I did this calculation. What did I do? Oh, I'm just checking to see that those 3 polynomials are linearly independent. So to do that, I fell back on the standard, which is to check, a linear combination equal to 0 and see if that forces the coefficients to be 0. Now, some things you should, we can assume, like the linear independence of the monomial basis. I've never proved that in here, right? Maybe that would be a good test question. Prove the linear independence of the monomial basis. How would you do it? Don't know? That's a perfect test question then. Let's see here. Just do that. So let us suppose that we have C1 plus, let me pay C0 plus C1t plus C2t squared plus dot 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 plus Cn t to the n equals to 0. I'd like to argue that all of the coefficients are 0. How can I do it? Because if I can do that, I've proved the monomial basis is linearly independent, yeah.
Assume one isn't a proof of contradiction.
Assume what?
Assume one is non-zero, a proof of contradiction.
Oh. I'll let you do that. I'm not going to do that. I try to avoid contradiction when I can. So for this to be an equation for a polynomial, this has to be true for all t, right? We can look at it as a function equation. So this is true for all t in the reals, right? Which means that you can do some things to it, right? Like you could evaluate it at a time that you like. You could differentiate it. These are things we could do. We could integrate it even if we wanted to, but I wouldn't do that. If I evaluate this at 0, what happens? So maybe give this thing a name, like f. F of 0 is what? C0, which is equal to 0, because this is the 0 function, right? So there's 1 down. Differentiate, yes. So f prime of 0 is equal to C1, which is equal to 0. And then f prime prime of 0 is 2C2, which is equal to 0. And this continues. The nth derivative evaluated at 0 is n factorial times c to the n, which is equal to 0. Right? If I had more time, I'd do it properly, but this is a review session. I'm trying not to just do this today. Of course, you could make it more rigorous by doing what? Like induction, perhaps. But this is kind of a silly place to do induction, honestly. Or you could also, I don't know, use Taylor's theorem, right? Because Taylor's theorem from calculus would say that the formula for Cj is the jth, the jth derivative evaluated at 0 divided by j factorial, right? But since this is the 0 function, this is equal to 0 for all j. So anyway, this is how I would prove the monomial basis is linearly independent. I didn't do it in class, but this was what was missing, okay? But you've been assuming it since like middle school, right? Every time you do ax squared plus bx plus c equals to something with numbers, you assume that you can, what, equate coefficients, which is our other characterization of linear independence, right? Equating coefficients. So if you could show a set doesn't have the equating coefficients property, that would prove it's linearly dependent as well, right? That's another way you could go. I don't usually use that. That's kind of awkward to use in proofs, right? Prove something's linearly dependent by proving it doesn't have the linear, the equating coefficients property. That's, to me, that's an unnatural way to proceed. I much prefer either showing there's a non-trivial combination or explicitly showing the linear dependence. All right, enough about that. Let's see here. How about this one? Trace of A is equal to 0, and so we're trying to find a basis, I think, here for this particular subspace. Now, so actually I said show it's a subspace and find a basis. Now here's the thing. If you're showing something's a subspace and you're finding a basis, don't bother to show it's a subspace. In the process of finding the basis, you're going to end up showing it's a subspace anyway. So like, don't waste your time showing it's a subspace. Just find the basis, because you will end up showing that the alleged subspace is the span of a set in the midst of the calculation, so that gives you a proof that it's a subspace. There's no need to, separately prove it's a subspace. So if I use the conditions here, the traceless and symmetric, then that gives me, the sum of the diagonals is 0, and then the off diagonals are matching, right? So that reduces, and then you, so admittedly here, there's a little bit of an art. You'd be like, well, wait a minute, how do you know for sure that you've chosen a set of linearly independent parameters to like describe the general A, right? So to be absolutely certain, you could take it and reassign it as a system of equations, do row reduction to remove all doubt. I never do that because I think it's just evident from the formulas that we write that you can't further reduce it. I've already taken full advantage of the symmetry equation and the traceless condition. There's like nothing more to do. And after I put that into place, I'm just left with these 3 parameters and then like these 2 guys, and I chose to write the first one in terms of the second 2. Now this is one choice. There are others you could make, right? You could keep these first 2 and then write the third one as the minus the sum of the first 2. Or you could do something funkier where you did some kind of weird thing with all 3 in such a way that it somehow still adds to 0. There's so many other things you could do, but that's what I did. And once I do that, then evidently A is in the span of these 1, 2, 3, 4, 5 vectors. Therefore, W is a subspace, right? Because it's the span of this set. Why is this set linearly independent? What happens if you put this linear combination equal to 0? What does that imply? It implies that A12, A13, A23, A22, and A33 are all 0. Because the only way A can be 0 is all of its components are 0, and hence these components must be 0. So we get simultaneously a proof of the linear independence as well as the spanning of that set. It's like, it's all there. You just have to argue it. As I do down here. I said it's clear. It's a proof. So, but it really is clear from the calculation, yeah? No joking. And the dimension is 5. Why? Because there's 5 things. I'll try to put at least something on the test with like Z mod 5 or Z7. I will try not to make something that requires like the full ensemble of the calculational monstrosity, which is the appendix. I mean, if you look at it, I give you techniques in there to calculate the inverse of a number mod some large modulus with the division algorithm. You are not expected to know that for this class. Like, you should be able to find the inverse in z mod n with just simple arithmetic. So I don't think I would give anything past probably 11 on the test, honestly. Because past that, it starts to get a little bit, it's not linear algebra, that's something else. But I do think this is fun, right? Because the question of how big the solution set becomes interesting, you know? Like here, you've got a span of 2 vectors in Z5. If we were over the reals, or the rationals, or the complex numbers, this would have cardinality of infinity, you know? I mean, it'd be huge, because you've got like a real or a complex or a rational parameter, pair of parameters. But here, you've just got 2 Z5 parameters, and as I argue, they're linearly independent. I like this, by the way, for 2 vectors. Prove linear independence of 2 vectors. There's a special trick here, right? If this is not a multiple of that, then they're linearly independent. And I think usually you can just reasonably eyeball it and argue it. So you can make that argument on your test too, if this is the situation, right? But you should actually make the argument. Don't make me make the argument for you. You make the argument. I read what you write, not what you think. So, you know. Anyway, this is dimension 2, but the cardinality actually is 25, because you can choose 5 different multiples of each one of those, and they're independent. That gives you 25 total things. Anyway, any questions before I just meander on through here? This one, like, by the way, my solution here is not optimal. I'm working far too hard. I was hoping it would be non-trivial. And if it was non-trivial, adopting the real notation would almost certainly be necessary to discover what the basis was as a real vector space. But it turns out that these 8 conditions conspire to just make everything 0. So it was the 0 subspace. This is even easier to see if you just use like A as A, B, C, D, because then that gives you the equation like A is equal to minus IA is the one thing, and D is equal to minus ID is the other thing. And if you use a complex notation, it's even easier to immediately get to that it's the 0 space. So, which was good for us because that gave us a chance to learn that the subspace of the 0 space is the empty set. All right. Right, which is linearly independent with span 0. So let's see here. Here we had a basis of 4 vectors. Find the coordinates of A, B, C, D with respect to beta. This is a pretty standard calculation, right? I just have to solve those equations for C1, C2, C3, the constants. And I do, and there it is. Hooray. And then I check my answer, and it works. Woohoo. This one here, I already did in class, sadly. I did that in class. That was an accident. You're welcome. This one here, 26, we were supposed to find a basis. All right, so how do we find a basis for a subspace? Like, I think we've had about, what, 6 or 7 problems now like this? Different varieties and flavors, but the question's always the same. How do you find the basis for a subspace? The answer is this. You take an arbitrary element in your subspace, and you apply the conditions to that element, whatever those conditions may be, and you see where that leaves you. Usually, you should be able to reduce the number of parameters to the actual number of parameters which remain. However many that is, that's the dimension. Each one of those parameters will allow you to like factor out, and whatever's next to it is going to be the basis. So it's a lot like the null space calculation from 221 if you think about it, what I'm saying. But that's what I did here, right? I took an integral of an arbitrary element, at squared plus bt plus c. I set the integral equal to 0 because I'm looking for that. That's my definition of w. And So that gives me this lovely equation here. And I solve for c. And that gives me this, which gives me that. Done. It's also clear that it's linearly independent because one's not a multiple of the other, right? So did I write that? I don't know. This is later in the homework. I may have been getting lazy. Or what was I asked? No, find a basis. I do need to argue it's linearly independent. I should argue it's linearly independent. I don't think I did that. My bad. Oh, there it is. Whew. No, it's close. I almost had to take points off this solution. My goodness gracious. That was close. I tell you. I'm a victim of my own legalism. Problem 27 is deeper. Problem 27 is deeper. It has things to think about. Things that could catch you off guard if you're not ready. All right. So the purpose of 27 is to explore the question of intersection of subspaces. Like, how do you find the basis for intersection? And so essentially part A is easy because W1 and W2 are both characterized by equations. How do you make both equations true? Just apply both at the same time, right? So if you think about that, that simply means that I have f of 1 is 0, f of 2 is 0. So by the factor theorem of high school algebra, I can factor out x minus 1 and x minus 2. And since this is a fourth order, arbitrary fourth order, what's left is a quadratic over here. I have no information about that because all I know is f of 1 is 0 and f of 2 is 0. There's nothing more to impose, right? That's it, end of the line. So work it out. It's a times x squared that, b times x times that, c times that, which gives me the basis, bop, bop, bop. Done. Although I do need to prove they're linearly independent, right? Which is, I hope, what I did next. You might be tempted to think that they're not linearly independent because it looks like one is x times the other and the other is x squared times the other, right? But remember, linear dependence is judged on the basis of the field. Multiplication by x is not a field multiplication, it's something else. It's a math 422 something else, okay? So there's my proof of linear independence. Since it's not 2, I can't use my multiple trick. I have to go back to more basic principles and say this plus that equal to 0. Work it out, equate coefficients. And I'm using the monomial basis, the theorem that the monomial basis is linear independent. I keep falling back on that in polynomial examples. So, and you can as well. You don't have to prove this in the test unless, like problem 1 on the test is prove the monomial basis is linearly independent. And if your proof for that is, well, the monomial basis is linearly independent, you said it in class, then I'll be like, that's funny, but no points. So, so like, obviously if the whole question is prove linear independence of the monomial basis, well, then you probably should do that. But short of that, you're free to use the linear independence of the monomial basis, for sure. And odds that you need to use that somewhere on the test, I would say they're high, right? Because the lion's share of our example are polynomial examples. Why? Because polynomials are easy. And they're abstract. Like there's something new. So that's the point. They're new. They're this course. They're not 221. Now, so as I look at this equation, my x to the fourth is just c1. X cubed, I've got a minus 3c1, a c2, nothing over here, so that's giving me this. X squared, 2c1, minus 3c2, c3, yeah? You don't actually have to multiply it out. You can write it like that and collect terms, right? Does multiplying it out make it more correct? That depends on whether or not you multiply it out correctly. And there's about a 30% chance under time pressure you're going to multiply it out wrong. Less writing is sometimes the better path. I mean, there's a balance to be struck here. I don't know. I've never found it as a student, but.
Just write the answer.
Now that's a question of academic chicken right there. Is the professor going to see?
The proof is the answer.
Okay, so problem 27 continued. The W3 was not given by an equation, it was given by a span. Right? So I can't just combine a span and an equation in a simple way. So what I do sometimes when I'm confronted with a problem like this is I convert a span to an equation. That's one thing I do. So you know, my span W3 is a linear combination of these two guys. And so what that means is if I have an arbitrary element in W3 like this, A, B, C, D, E, it's got to be equal to C1 times that plus C2 times that, right? That's the structure. And then my goal is to find equations on A, B, C, D, E, which describe the span. And the name of the game is to eliminate C1 and C2. And I do that fairly easily because, well, B equals 0, that's simple enough. C equals 0, that's simple enough, right? And then I've got D as C1, and I've got A as C2, so then I've got E in terms of, well, A and D. So, yay. In the abstract, though, it's kind of scary, right? Because we got 1, 2, 3, 4, 5 variables, A, B, C, D, E, and I've got, what? C1, C2, that's 7, right? 7 unknowns. How many equations? Apparently 5. So 5 equations and 7 unknowns. But they're linear, so you can solve it. As I did. Did I use row reduction? Certainly not. Why? Because it would be completely unhelpful, right? So just because you have a hammer, don't let everything look like a nail. Anyway, so there's the W3 written as an equation in terms of equations like that. And so if I want to look at W3 and W1 intersected, then I can apply the equation that the equations I just found to describe W3 together with the ones that describe W1. Now at this point, I have to face the music because I've got 4 equations and 5 unknowns, and they're not that nice. So I'm just, to be safe, I'm going to use row reduction. You know, it just got a little bit too much. Now you probably could see through it without row reduction here, but I did row reduction. And after all that, I finally learned that B, C, D are 0, A is equal to minus E, and as such, f of x is just a multiple of x minus x to the 4th minus 1. All right. Now, there are other ways to do this problem. This is just a way. But anyway. Problem 28, part A is like a really good test question. This is a pretty standard test question. Given linear independence of a pair of vectors, prove linear independence of this other pair. Like this is, it's a nice question. It's not super difficult calculationally, and it really does pretty well test your understanding of what linear independence is in the abstract. Because U and V are completely arbitrary here, right? So it's like, it's got nothing to do with polynomials or matrices or functions. It's just that, you know. Part B is tough. One of the directions is tough. The other, like, I think the converse direction, no, wait a minute. I think the forward direction is easy in both cases, but the converse direction for part B is kind of a bit much. Like I had to think about it. My bad. Where am I? So anyway, my solution is lengthy here. So I had a proof by contradiction there. I don't really care about it. I think the other proof is better. Listen, I'm going to go on. We got other stuff to talk about today other than this homework. So 29. This is a good problem. Like show that we have linear independence of exponentials with different, values of r. So here again, the key is this is a function space. So you want to prove things about function space, you can use the fact they're functions, which means it's true not just for one value of t, but all. So because of that, I can do things like differentiate it, right? Because I know how to differentiate exponentials from calculus, and you're still allowed to. So differentiating that gives this. So if I plug this one in, plug in t equal to 0, I get c1 plus c2 equal to 0. Plug t equal to 0 down here, I get c1r plus c2s equal to 0. Now I've got two equations and two unknowns, and I can hit it with the full force of my 2 by 2 inverse formula, woohoo! And c1 equal to 0, c2 equal to 0 pops out, which means that they're linearly independent. Now there is, as I say down here, another way you could do it would be just proof by contradiction. Suppose they're linearly dependent, then one has to be a non-zero multiple of the other, but then by algebra, k is the ratio of this and that, which by algebra is this. R not being equal to s, this is a function of time. So e to the non-zero multiple of t equals to a constant is absurd. Contradiction. Therefore, they must be linearly independent. That is also totally legitimate argument here that could have been given. So you got choices, which means I have to think when I grade your test, right? I actually have to think. I can't just assume your solution's not my solution. It must be wrong, That's why they pay me the big bucks. So, where was I? Let's skip over to the quiz. Oh, not that. Ooh, definitely not that. Quiz 2, all right. So I hope you like problem 1. I'm kind of proud of this one. I'm a little bit proud of this one. A little bit of personal history on problem 2. There was a semester I gave no one the grade of A in linear algebra. The reason for that was on the final exam, I gave this problem to a class of like 20 people, and nobody got it. I'm like, I can't in good conscience give anyone in there an A, because an A student should knock this out of the park. All right. It wasn't like the first time we'd ever done anything abstract in that class either, right? I mean, it was somewhere between 221 in this class, but it was still a lot of proofs. So, but I think that's not going to happen in here, right? But that's an anomaly. Like, it was so surprising to me that a whole class couldn't get it. So I think that's the only time I've ever had to do that. Hopefully it never happens again. But anyway, so very simply, 0 is in both, right? Both subspaces, therefore it's in the intersection. And if I take two vectors that are in the intersection, that means they're in both spaces, which then means a linear combination is in each of the spaces, which means it's in the intersection. Therefore, the intersection is closed under linear combinations. So by the subspace test, we have that the intersection of two subspaces is a subspace. Here's a question for you. The book has some good study questions. Like the true-false questions in the book, those make really good study questions. If you look at, like, there's like, like in the vector space section, it's got like true-false at the start. There's a ton of like great little questions in there to think about. Here's one. Is the union of two subspaces a subspace? Like, what if, intersection's a subspace. What about union? How's that go? Here's one. Let me show you why that fails, right? Think about this. In the plane, the y-axis is a subspace, right? The x-axis is a subspace, right? What's the union of the x and the y-axis? Well, it's the x and y-axes. Is that a subspace? Definitely not, right? Anything you add, if you take 1 point here and 1 point there, you add them, where you go? Yeah, you're not on the axes anymore, right? So no, the union of two subspaces is probably not a subspace. It is in one case. What's that case? They're the same? That's
one's a subspace of the other.
One's a subspace of the other.
Or, subset of the other.
If one is
Would be subspace.
if one is a subset of the other, then yes. But I believe that's if and only if, actually. So like asking yourself questions like that, that's those are good things to think about. We remember image and null space, column space and null space from 221, I hope. So we've been calculating kernel and image lately, right? And so the deal is, if the image is not the whole of the codomain, it's not onto, right? And if the kernel is non-zero, it's not one-to-one. But we have a theorem, linear transformations one-to-one if and only if the kernel is zero. That is something you should be able to prove on the test, right? Any of the theorems that I've been able to prove in class without a lot of difficulty, those are like reasonable test questions, all right? So, because if you look at the level of difficulty of the in-class proofs, many of them are actually easier or similar to your homework in difficulty, right? So, now of course I have to set the thing up for you and I have to tell you what you can assume, things like that. And if I don't do a good enough job doing that on the test, you should come and ask me, are you wanting me to assume such and so forth? And I will tell you, all right? So this is a nice problem. And because this one here, like, we really have to, well, that's the other thing I should mention is most of you have started to adopt like how to do proofs with components. One or two of you is still doing like plus dot 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 stuff. That would be a problem if I was to ask one of those on the test, right? In many previous years, I have asked, prove the trace of AB is equal to the trace of BA. I have asked that many a year. That's a good problem that tests, component calculations. This is also a good kind of problem to test component calculations because I don't think you can really do this without components. And if you didn't get this, that's okay. That's kind of like the point of homework, was to mull over this and see if you could get it. I don't think everybody's going to get this right off. Like, this takes some time to think of. But anyway, so if we think about an antisymmetric matrix, we can prove that the diagonal components are zero, right? And as such, we can write the whole thing as a sum over I not equal to j. But if you think about that, there's two cases. Either I is less than j or I is greater than j. So we got those two pieces. But then I switch the, relabel the sum just to make progress here. All right? And then once I've done that relabeling, I'm going to use the antisymmetry, the skew symmetry of the matrix, to get ALK is equal to minus AKL. And after I do that, then instead of writing it, I also did here, right? I went from I less than j to k less than l. So I flipped the, so I relabeled the sum like such, and so I made the pattern match up. At some point, I have aij on. Oh man, come on! I didn't touch. Stupid. So I have aij on both factored out, and then there you go. That proves that these guys span the set of antisymmetric matrices, all I less than j. So this proves it's a spanning set, and if you put this equal to 0, we also get linear independence of these animals. How many are there? Well, I have a very complicated way of calculating it on the next page. You want to see? This is how not to do it. So if you look at it, the first choice, I've got n minus 1 choices. Then the next one, if I put I equal to 2, I got n minus 2 choices. All the way up to I n minus 1, then I got n minus 1 choice. So the number of choices is that, where there's n minus 1 fold summands, which I can rewrite as such. And then by Gauss's formula, which says that the sum of the numbers from 1 to n is equal to 1/2 n times n plus 1, which when you apply it to n minus 1 gives you this. I get this, which gives me this, which gives me that, right? This is the wrong way to count here. How should you do it? There's a way easier way to think about this. By the way, here's what I would have done as a student to start this whole problem is I would have worked these two things out to see what's going on, and then from that, use the higher, fancier notation to try to understand more. So the easier way to like do the counting is if you think about it, n squared is everything, right? You're removing the diagonal. How many is left? N squared minus n, right? Half are above the diagonal you deleted, half are below. So the number of things in the basis is n squared minus n divided by 2. That's the way to count, not what I did. So, all right. You can ignore this, is what I'm trying to tell you. There's a better way to count. Anyway. How about this one? Here we're asked to calculate the kernel, the image, the nullity, the rank, and verify the dimension theorem, which is also known as the rank nullity theorem. So, first of all, I was supposed to show that T is linear, so I did that. And we assume that we know differentiation and integration are linear in here, right? Yeah. So rules of calculus we assume we know in here, just as a point of, baseline order. That might not be true in like real analysis, for instance. In real analysis, there's probably places where you're not allowed to assume things you know in calculus, because you're building things from scratch in there. It might be inappropriate to use calculus in the middle of real analysis. But in here, we're allowed. So anyway, I proved linearity. And then how do you calculate the kernel? You take an arbitrary thing, you feed it to the linear transformation, and you set it equal to 0, see where that takes you. Again, monomial basis, linear independence of monomial basis gives me these conditions, which apparently gives me A equal to 0, B equal to 0, and C equal to 0. Hey, the kernel's 0, which means this is a injection. It's 1 to 1. Right? And then what? Well, I can also see that the image, by the same formula, is the span of these three things, right? So, and I guess, I don't know if I've proved linear independence of those three things here. There might be a gap. How do I know there's a linearly independent? I can cipher that from the rank nullity theorem, if nothing else, right? So
nothing times x will give you x squared plus 1, and nothing times x will give you x cubed plus 2x.
Yeah, I think you're right. I mean, it is somewhat, the fact that these have different degrees, intuitively speaking, means you're right. But here's a way I could argue if I didn't see that. I could be like, well, rank nullity theorem, the dimension theorem says the nullity of T plus the rank of T has to be what?
The dimension of V.
It has to be the dimension of V. What's V here? Well, V is P2, which is dimension 3, right? I've already proved that the nullity is 0, because that's the dimension of the kernel. I know the dimension of polynomials is 3. So 3 plus what equals to 3? 3. So this is a spanning set for the image with 3 things in it. It must be a basis by logic. Yeah.
But aren't you trying to verify that theorem by doing these calculations?
Fair enough. So I should prove it's linearly independent. Take away my points. I don't know. There's like this question is like a laundry list. There's so much. I got lost. I'm sorry. It's like this problem's like, oh, what are these instructions? What have I done? I'm just glad I didn't assign 2 of them, Goodness gracious. So problem 6 is, again, pretty straightforward. You take an arbitrary thing, let the linear transformation do its thing, set it equal to 0 to find the kernel, look at its general form to understand the image. All right, let me skip past here. These were nice. These are really nice. This like problem 7, it seems scary, but like when you actually sit down and work through it, think through it, it's not bad. So I'm not going to hurry through that right now. And here, we just have to like sort through the basis. So when I have, this is my basis, and I have, this is the vector I'm finding the vector of, I just have to think, how do I get it as a linear combination of these, right? So I need one of the E11s, And then I need 1 of which? 1, 2, 3, 4, 5, the 6th, right? 1, 2, 3, 4, 5, 6. I need an I in the 2, 1 spot. See that? That's why there's a 1 here. And this one, I need an I here. Where does that come from? Well, that comes from this, right? And this comes from that. And that comes from that, which is why I've got this pattern here. So do make you, if you didn't get this problem, it's important that you sit and mull over it until you understand it. You really do need to have a clear mind about how to find coordinates with respect to a basis. Like there definitely are questions about this. And if you don't have it, if you're wasting a ton of time learning that on the test, that is a bad place to be. You need to make sure you nail down coordinates and vectors like that. That does matter. Let's see here. I'm going to post this solution, but please understand problem 10 is currently wrong because I inadvertently changed the definition of gamma like mid-problem, so let's ignore it. So I have a really beautiful this is a wonderful solution. It's so pretty. It's 2 pages. It's really nice, but it's also wrong. Anyway, so you guys have any questions? I'll just probably end class here, but. Oh, problem 13 was on the quiz, and I will grade it, but this would not be on the test because I did not cover the transpose of a map in class. So like I left it here as a homework problem, but it won't, this particular construction, the transpose of a linear map, that I wouldn't put on test. Dual space might be on the test, dual basis, like the thing I proved about the dual basis, that stuff. You know, I might have a question about that. By the way, if you didn't get the isomorphism, make sure you look at these. They're really not complicated. Like you just literally have to write down the element that you're trying to map and just follow your heart. I mean, that's like Hezekiah chapter 10, verse 7, right? Follow your heart. So, just like that, yeah. Anyway, I should shut up. Have a good weekend, guys. Enjoy your carnival or whatever. Beware of the carnies, though. Yeah. They're all criminals, right? Oh, wait a minute. Do I have to edit this now? I don't know.